Welcome back to Arxflix. Today, we're diving into a comprehensive survey on model-based reinforcement learning, or MBRL. The research paper we're discussing is Model-Based Reinforcement Learning, a survey. It provides a well-rounded introduction to how MBRL integrates planning and reinforcement learning to optimize sequential decision-making, commonly formalized as Markov Decision Process, MDP, optimization. Here's a figure showing the connections between planning and learning in MBRL. We will use this illustration to dissect various aspects of MBRL. Model-based RL integrates planning and learning by utilizing a dynamics model and approximating global value or policy functions to solve MDPs. Unlike model-free methods, MBRL learns a model of the environment to improve learning efficiency and decision-making. One of the first and most crucial steps in MBRL is learning the dynamics model. This involves predicting state transitions and dealing with challenges such as stochasticity, uncertainty, partial observability, non-stationarity, multi-step prediction, and state and temporal abstraction. This figure shows different types of dynamics models, including forward, backward, and inverse models. We will focus on forward models as they are the most commonly used in MBRL. The next major component involves the integration of planning within the learning loop. This involves deciding, firstly, where to start planning, uniformly across states, at visited states, or prioritized start states. Secondly, how much budget to allocate, real-time steps before planning, and the effort for each planning cycle. Thirdly, how to plan, whether to follow discrete or gradient-based planning, forward or backward planning, and how to deal with uncertainties. Fourthly, how to integrate planning, using learned value or policy functions as inputs to planning and planning outputs to update these functions. This figure illustrates the breadth and depth considerations for planning iterations. Understanding these factors can help you balance exploration and exploitation effectively. We also have implicit MBRL, which optimizes elements of planning through a differentiable computational graph. These include, firstly, value equivalent models like mu0. Secondly, learning to plan, as seen in MuxNets. Thirdly, combined approaches like Treecon. Here's a snapshot of different implicit MBRL approaches. These methods wrap model learning and planning into an end-to-end optimization framework. MBRL has several significant benefits. Firstly, data efficiency. By effectively planning, MBRL can make better use of available data, reducing the need for extensive real-world sampling. Secondly, targeted exploration. Model-based approaches can guide exploration more effectively using state-based or value-based strategies. Thirdly, transfer learning. Models learned in one task can be transferred to another task with similar dynamics, accelerating learning. Fourthly, optimality. Planning can lead to better long-term performance, especially with a known model. Fifthly, safety and explainability. Being able to predict future states can make MBRL safer and more explainable. This figure summarizes the benefits, emphasizing how MBRL can enhance data efficiency, exploration, transfer learning, optimality, safety, and explainability. While MBRL is promising, it has challenges like computational complexity, dealing with model uncertainty, and optimizing the balance between planning and real-world data collection. Future work could focus on improving asymptotic performance, hierarchical learning, and better exploration strategies. That wraps up our overview of this exhaustive survey on model-based reinforcement learning. If you're diving into the field of MBRL, this paper is a must-read. Make sure to subscribe to Arxflix for more in-depth research paper breakdowns. Thanks for watching, and see you in the next video. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.